You're listening to Carbon Removal Newsroom, a weekly show about current events in the world of carbon removal, from technology and innovation to policymaking and job growth. Brought to you by Nori, the carbon removal marketplace.
Welcome, everybody, to the October 24th edition of Carbon Removal Newsroom. Today, in a bit of a throwback, we're going to do a science-focused episode. So I'm really happy to have Hamed Sanei, professor with the Department of Geoscience at Aarhus University and the director of the Lithospheric Organic Carbon Lab there, joining me. Hello, welcome to the show.
Hi, thank you very much. Thanks for having me.
Looking forward to the conversation, and I'm Radhika Mulgavkar, Head of Supply and Methodology here at Nori. So we are going to talk about biochar today. As most of our listeners probably know, biochar represented 92% of permanent carbon removal sales in the first part of 2023. The great things about biochar is it's technologically ready, it's accessible by a large share of businesses and populations, and it's relatively low tech compared to other types of permanent methods. A recent report found it could one day deliver 3 gigatons of CDR annually. More investment money is flowing to companies doing biochar, and it has become a staple of CDR portfolios among buyers who are diversifying. Not only that, but it's an old technology, probably thousands of years old, and works as a soil amendment that helps crops productivity. It can be made from a huge variety of biomass types, and the potential uses are just as numerous. But there's always been sort of this overarching question about biochar, which is the carbon removed from the atmosphere by biochar stored permanently, or will it return to the air, and in what time frame? It's been a surprisingly difficult question to answer, and there are many variables that determine how permanent the removal is when biochar is made. However, there's been some new research with some great conclusions, and so we're going to be learning about that today. And I will start with my first question, Hamed. Can you give us a brief overview of your research around biochar and its potential for carbon removal?
Okay, I've been working on what you call it biochar, but what we call them inertinite in our field of study for many years. So for geologists, what you call biochar is really nothing new. It's been around and studied in carbonaceous rocks, the rocks with organic carbon like coal, shale, any sedimentary rocks. These we call it fossilized carbon or char. They've been around for the whole duration of the geological history of Earth, and geologists have been studying them for almost near a century. So I've been working on this subject on the carbon cycle for many years, for the whole duration of my academic life, over 20 years. But recently, in the past couple of years, I realized there is a big need and there are some knowledge gaps in the biochar in terms of CDR. And so we thought this is a good time to enter in this subject and bring a new perspective into this subject.
So can you tell me a little bit about why there's been uncertainty in the past about the permanence of carbon removal using biochar?
Well, I have my own theory. I think when biochar as an industry started, the name, I don't know why they chose that name, biochar. I think it was partly marketing strategy to call it biochar. But the term bio immediately bring the attention of a lot of bioscientists. And then they've dealt with the biochar as a biological matter. And then when you deal with biochar as a biological matter in biosphere, the length of your study, the scale of time is much shorter, right? But the objective is geological permanence. Is the actual permanence is much longer than what we expect in a biosphere. So I think from the beginning, it has been a very misunderstood kind of product or the field of science, because people have tried to study biochar in a certain experimental work that has been designed for several years, and I tried to see how it is being degraded. But the objective was to establish the permanence. So, we don't have a luxury of time to experiment for 100 years or thousands of years. So most of the studies that try to kind of replicate the degradation of biochar in a few years, and projected. So it's basically as you try to predict things based on their pattern, based on their trend. And this is where the problem comes. Whether if you change the name of biochar, what the geologists call it inertinite, then you would see these are very common in a geological time. That immediately would suggest that these type of carbon have survived many millions of years. So there are two ways of looking at things, try to look at things in a shorter scale, or you see, okay, why have these been around for many hundreds of millions of years? And why don't we compare those to what you're producing and see if they are similar or not? So it's how you look at it. And I think that's where the big discrepancy in the question of permanence is coming from.
God, I love that. I'd never heard that. So thank you. All right. So I want to kind of dive into your research. Can you describe to us the structure of your recent studies and what the methods you've been using to study inertia? I don't know. I'm probably not saying it right, but biochar.
Essentially, it's the most stable form of organic carbon in the Earth's crust within the sedimentary basins. That means it is the end product of carbon cycle, organic carbon cycle, just before graphite. So when the organic carbons are buried in the geological system, everything will eventually be buried, either in the soil, either in the sediments. Everything will be subject of geological cycle. So these carbons, they keep becoming more stable. Of course, significant portion of it will be lost due to biological or temperatures or many different natural processes, oxidations, you name it. But it doesn't vanish into the thin air. It doesn't immediately disappear into the CO2 or methane. There would be a certain fraction of organic carbon that will be left behind. And when it is left behind, it becomes more and more stable. So the end product of this carbon evolution journey would be what we call it inertinite. So it's a very well-known thing. We know what's the composition. We know how they look like. We know their optical properties that are under the microscope, how they look like. So it's kind of like minerals, when you say carbonates, you know what it is because it has a certain composition and it looks in a certain way under the microscope. So geologists know immediately how carbonates look like. They can tell the difference between carbonate and pyrite or other kind of minerals. Inertinite is exactly the same. It has a very typical characteristics that has been well studied. So why don't we compare biochar to the inertinite and use that as a benchmark? That means if it has reached the characteristics of inertinite, let's accept that this is the most stable form of organic carbon. We do that in a CCS. We do that in a other form of CDR, like mineralization, where the CO2 is converted to the carbonates. When CO2 is converted to the carbonates, we accept that as a permanent storage. Why? Because we know that carbonates are the mineral carbon and they are the most stable form of inorganic carbon in the Earth's crust. So inertinite is the same thing. It is the most stable form of organic carbon. Okay, that's the only difference. It has an organic root, but there is nothing biological about biochar or inertinite. It has really lost all form of its biomarkers. So it's a real carbon polymer with a natural origin. But the way we look at it, it's an extremely stable form of carbon polymer that we are dealing with. And I think that is back to your previous question, that's where the misunderstanding comes. We look at biochar as a biological matter, whether we look at it as a extremely stable carbon polymer, that would be the end product of carbon cycle in Earth's crust.
So is your research comparing biochar to inertinite to find at what point the two kind of converge, or what are you looking to publish around?
So one way is exactly to use the well-studied characteristic of inertinite as a benchmark. So when we have a biochar is not a homogeneous material. Two biochars may not look the same, may not have the same composition. They may be very different. They have a different origin, different temperature that they're for. So what we can say is whether or not they are reaching the level that we call it inertinite. Are they becoming, as you said, converging or becoming compositionally and microscopically, they're becoming identical to inertinite. So we use the benchmark as acceptance for the permanence. So that means once they are inertinite, we can call them permanent. So you see, then we don't need to measure the how many years of permanence. We're talking about millions of years. That's what we are talking about. That's one thing. But now you may ask, okay, well, how do you measure how many years? Give me a number, like 1,000 years, 2,000 years, 300,000 years. Like, what are the numbers? This brings us to the other research that we do. So, which is basically kinetic reactions. That's a fancy word for it, but I'll make it very simple here. You see, there are two ways you could deal with any kind of reactions. Either you give a reaction a long time, like sit there and measure things for thousands of years or millions of years until the entire carbon is degraded and vanish into the atmosphere as a CO2, right? That never happens. People are trying. There has been 120 studies, as far as I know, try to degrade biochar with bacteria, and they measure the amount of loss of carbon. The longest has been 8.5 years, 9 years. They only degraded about 6% of carbon. It never reaches beyond that. It's a pretty low number. So we don't have a luxury of time. We cannot sit there and wait until we degrade 100% of them. So the other way you could do is increase the force of the reaction, make the reaction more aggressive. So then it becomes much shorter. You could degrade the entire biochar in a much shorter period of time. Okay, so that is, as far as I know, nobody has done it with bacteria. I mean, bacteria just simply you cannot increase their force of reaction. But what you could do, you could use oxidation with the heat or combustion. So basically, combustion is a very strong form of oxidation of carbon. Nothing is in nature is stronger than combustion. So then what we do, we increase the temperature of the combustion or decrease it. You do it at a many different temperature. And then we measure the amount of time that it takes that all the carbons break down. So when we do it at a different temperature, a different force of reaction, then we establish a trend for time. So then we can actually say, well, what if you reduce the temperature or force of the oxidation reaction to, let's say, 20 degrees centigrade? Then how long does it take? So you would establish the trend of time based on change in the force of the reaction. So we have done that. We are doing it right now. It's a very kind of recent work that we just finished, and we are submitting the paper in days. So I can tell you the results of kinetics is we're talking about millions of years. And that's exactly what we expect. If you have a pure inertinite material, if your biochar is certified as inertinite, that means it has exact characteristics of what geologists call it inertinite, we're talking about half-life of, the shortest would be half-life of a million years. And that makes perfect sense for any geologist because we have billions of tons of organic carbon stored in the sedimentary basins and sedimentary rocks. The question is, how do they survive if carbon is lost on the surface within 1,000 years or within 100 years? Then nothing would pass the time of this very reactive or very aggressive reaction on the surface. then nothing would go through the geological kind of cycle of carbon, where we know it happens all the time. A lot of carbon is buried, and it will actually saved and preserved during the geological evolution. So it has to be something within a time frame that we have measured and we have estimated. So this is something that's very new. It will be published soon, and you will see the results soon. But essentially, these are the two things that we are doing.
So that leads me to a couple of follow-up questions for you. One, you talked about, obviously biochar has different characteristics based on the stock, the temperature it's created at. So are there certain types of biochar that do better or get to inertinite faster? And also, how does biochar get to inertinite? Is there other processes that are needed, or is it just time or heat or pressure?
Well, anybody who likes a steak, a well done steak, would know these things. So, for most important thing is the temperature. You need the high anything above 600 degrees would make the uh, biochar, more susceptible to reach the inertinite. Okay, it's a well calibrated work that we know these things. The second is the amount of time that you expose the feedstock, the organic carbon, to the heat, right? Your steak, if you let it sit there long enough, then all the way through it gets cooked. And so same in biochar, then the aromatization, the alteration of carbon would take place if you let it sit there long enough. So it's called residence time, heating residence time. So you need longer. And the third one is the size of your steak, or in this case, is your feedstock. So if they are much chunkier side material, so it takes longer for the heat to dissipate inside the organic matter. So the smaller particles, the higher chance that you get a very homogeneous kind of inertinite. So these three are perhaps the most important thing. There are other minor things. It depends on, of course, type of feedstock is extremely important. If you're doing flash pyrolysis or gradual pyrolysis, all of these are important. But the three that I told you are probably explain most cases.
I'm never going to look at a steak in the same way. So, are there other processes that lead to inertinite? Are there other things outside of biochar that people within the CDR industry should be thinking about or exploring?
One, there are other things. For instance, you would like, as I said, you would like to have a very homogeneous inertinite. Let's forget about the scientific terms. In a more kind of a casual way, you want to make sure you get a perfectly charred material. We call them biochar, but that doesn't mean everything in a biochar is perfectly charred. If it's not charred, what happens when you put it in a soil? The bacteria, they're very selective. They're very choosy. They're like us. They would start degrading or eating the most reactive or the most labile form of organic carbon. So they start degrading those ones. But if you make the material that's perfectly charred and it has reached the characteristics of inertinite, then we have a pretty nice material that could be very well characterized as permanent and as the most stable form of organic carbon. There are other things, for instance, some of the hydrocarbons that are being generated during the formation of biochar. There some of the materials are released as a hydrocarbons. So they could get trapped within the biochar during the cooling period, for instance. These are just the minor technical things that could happen. In terms of the amount, would be very small amount. But if you put it in a soil, it would be degraded. Those hydrocarbons would be degraded fairly quickly, and it would give you the impression that, oh, these materials are highly degradable. But I can assure you, after loss of 2-3% of carbon, it would stop there. Once it reaches the inertinate material, the degradation would not continue after that. So you would reach a plateau when it comes to the degradability. So yeah, I think the most important thing, if you're merely talking about stability, is to reach the characteristic of inertinite that's controlled by maximum temperature, the residence time of the heat, and the size of the particles. These are the most important things.
So, w- what you said, inertinites found all over the globe. It's a very common substance. So, if a person were to create perfect inertinite, and what do they do with it? Do you bury it? Like, I know it wouldn't work as a true soil amendment from how you just described it. Where do you find it, or what do you do with it once it's created, do you think?
I've looked at now near 70 uh, biochars that are currently being produced commercially from different companies, almost all of them from Europe, with the exception of two of them. I can tell you most of them are overwhelmingly, they produce pure inertinite. So most biochars are inertinite, in fact. Only, some producers that they need to a bit tune their recipe and they make a nice, well done steaks. But most of them are producing. So the bio, you could very well make them synonymous to inertinite, unless they are not charred properly. In that case, it would be semi biochar. We shouldn't even call them biochar if they're not charred perfectly. So the ones that are produced at a lower temperature, they have higher tendency to be kind of semi-biochar or semi-inertinite. But anything above 600 degree, any biochars that produce at the 600 and above with a decent residence time, a heating residence time, the likelihood to be pure inertinite is over 90%.
So, looking forward, this is my last question for you. I really appreciate this last half hour because you really expanded my understanding of biochar. I had no idea how this worked. But looking forward, what do you one see your research where you're looking to move, your research forward? And two, what are the things you believe the biochar industry within CVR needs to start thinking about to really help promote what you're learning and what you're realizing about the stability of biochar?
But if we are really serious about the CDR, the biochar is more than an industry. I teach carbon cycle to my students, and I always tell them the problem with the climate did not necessarily start when we began to burn coal or fossil fuel. It really started long before that, when we started learning how to make fire. It's combustion. You know, Combustion in the nature doesn't happen very often. Yes, maybe forest fire, but it's a relatively a rare occasion. Combustion started by humans for making food and all other things, and then industry and you name it. And that is the process that we invented, and we make it much more efficient. We're getting so much better at it. We're getting biomass combusted to almost 100% of biomass is combusted to CO2. I mean, in nature, nothing like this happens. If you go see a forest fire, maybe a percentage of carbon is lost as a CO2, but then the rest are char. They're going back to the earth. So nature has a way of keeping things behind, to go back to the geological cycle. But we're very good at combustion. We're burning everything into the CO2. So, that's a problem. So the bio or making a biochar is a really good step to correct that behavior. That we don't combust everything to CO2. Get the energy, leave the carbon behind to the earth. And that is what I like about it, because to me it's a true nature-based solution. I know some people may not call it nature-based solution, but I think it is a nature-based solution because that's how nature works. Nature would get the energy, either bacteria or you name it, get the energy out of carbon, but leaves substantial amount of carbon behind to the geological cycle. So I think we need to really pass this mindset that, well, how many years of permanence, is it 100 years, 200 years, 300? I think this is madness. We need to have a benchmark. The benchmark, if it is inertinite is a maceral. Maceral is like a mineral, basically. Mineral is inorganic, maceral is organic. We never question carbonates are being degraded. Once we turn CO2 into the mineral carbon, we say it's permanent. We store carbon geologically. We should think the same way. Once biochar is certified and reach the benchmark of inertinite, we should move on and study or be worried about other aspects of biochar, how it would help crops, maybe the toxic material, if there is anything, or if there is other problems that we should be able to solve. So I think we really need to pass this issue of permanence by accepting this benchmark. And if we reach the benchmark, we should be able to get the full credit for the storage of carbon.
I guess I said this is my final question. Where's your research going next? I'm just curious where you're looking to focus as you move forward.
Well, after these couple of papers that we are releasing, in our field of study is nothing controversial, but I hope our colleagues in bioscience and soil science would also see where we're coming from. I am really hopeful that we pass this kind of a stability issue. We issue a guideline for a benchmark of a stability and really pass and focus on other aspects. Like, for instance, PFAS or the spontaneous combustion for transportation of biochars, or how it could be more beneficial for soil, retention of water, nutrients, and those kind of things. We should really start working on the application of biochar to make sure it's a safe application. And of course, in terms of the engineering aspect, how to make the process more efficient, produce better energy, produce better biochar. So I think this is the area that we should be working on, and I'm hoping to work on that in the next few years. And of course, it's not me only. I have to tell you, I'm just a spokesperson of a very nice big group. My colleagues in Geological Survey of Denmark and Greenland, based in Copenhagen, my very good colleague, Dr. Henrik Ingemann Peterson, he's my collaborator who is working very closely with me. Lots of young researchers in our lab that are working on these issues very intensely. And we have also received funding in Denmark from Geological Survey of Denmark and Innovation Fund. So, and of course, EBI, European biochar industry, and some producers of biochars, individual producers, and other academics that are working with us. It's a group effort, but we really hope that we all come together and reach some kind of understanding that we should move towards higher priority issues if we try to get serious about climate and CDR.
Well, Hamed, you're an excellent spokesperson for them, and I wish I could take your carbon cycle class because I think it would teach me a lot. But I really appreciate having you on and all of your insight, and best of luck to you in your research and really helping get this message out to folks about, because I couldn't agree with you more, like looking at it from a benchmark and a storage like geological storage perspective makes so much more sense to me than the way we're trying to approach it now. So thanks so much for your time.
Thanks so much for listening to Carbon Removal Newsroom. If you like the show, the best way you can help us is by giving us a great rating and review in Apple Podcasts, following the show on Spotify, and by sharing the show on social media. Tell your friends and help us spread the word about what's happening in the world of carbon removal.